Hello, in this video we're going to talk about the wave-particle duality of matter. So the background here we talked about in the previous video is that in some experiments light behaves like particles, and in other experiments light behaves like a wave, and we call this the wave-particle duality of light. So in 1924 de Broglie reasoned that matter can do this also, and turns out he was right. The ultimate equation, the modern version of his equation, is down here, that the wavelength of some particle that's moving, that's matter, is related to Planck's constant divided by the mass times the velocity. And sometimes you'll see the denominator of this equation as just momentum, which is mass times velocity, but I like to split it out like this. Okay, so the wavelength of some matter particle depends on its mass and its velocity. So this equation is valid for all matter. The left side of the equation tells you about the matter as a wave. The right side of the equation tells you about the matter as a particle. So at first glance, this seems really weird. You're telling me that my hand is a wave? Yes, I am. It's just that the wavelength is so undetectably small for an object as big as your hand that you're never going to see it. Since the mass is in the denominator here, once the mass is bigger, the wavelength gets smaller. But if you have something like an electron, or maybe even a neutron or some small particle like that, then you can start to detect the wave-like behavior of that particle. So an example, and these are calculations that I want you to know how to do, if anything because it's an excellent exercise in dimensional analysis, and then it also tells us something useful about the world we live in. Okay, so kind of a ridiculous example. What's the de Broglie wavelength in nanometers of a 2.5 gram ping pong ball traveling at this velocity? Alright, so you go about this by first starting with the equation, which here I wrote in the kind of compact form, but again, what this really means is I'm saying equals h over mass times velocity. Alright. So now let me list out some of these things. So Planck's constant is in joules per second, m is the mass, and you can put it in grams, but that's going to get you into trouble later. So for this problem you'll put it in kilograms, and you'll see why when we get to working out the units. Velocity is in meters per second, and then we're going to need the definition of a joule, and you'll see why. Okay, so if we plug things in here, here's Planck's constant on the top, then on the bottom we have the mass and the velocity, and I already took the step of converting the mass into kilograms. Okay, so now it's just straightforward, solve, right? And then you get the wavelength. Sure, okay, so we solved, and then, however, our wavelength comes out in joules second squares kilograms meters. That's not a wavelength. The wavelength needs to be meters. So we have some work to do with the units. So here's where we use the definition of a joule. So I just took the joule and substituted it in here for where we had joule before. Alright, now we can go about canceling some of the units here. So the kilograms cancel, the second squared cancel, and then out of the meters, what you're saying by meters squared is you're saying meters times meters, and then on the denominator you have meters. So that means one of these meters cancel and the other one doesn't. So you're left with just meters on the top of here. Alright. So, now since you're left with just meters on the top, you can take that same number and say that this is your wavelength in meters. Great. Now the problem asks for the wavelength in nanometers. So here's your conversion from meters to nanometers down here. Remember 10 to the negative ninth goes with the base unit. Alright. And this equals 10 to the negative 23rd nanometers. Well, remember light is a pretty small wavelength, like visible light, and that's several hundred nanometers. So here we're at 10 to the negative 23rd nanometers. You are never going to be able to detect the wavelength of a ping pong ball. It gets kind of to be a ridiculous thing that you would even calculate this. However, as an example, an electron traveling at 1/10 the speed of light, its wavelength is 0.024 nanometers. That's still small, but it makes it excellent for imaging. And this is the reason why you can have electron microscopes that allow you to see things that are much smaller than you could ever see with a normal light microscope. It's because electrons have a wavelength, and it just happens to be just a few orders of magnitude smaller than visible light. Okay, so another example. I'm going to encourage you to pause the video and try the example, and make sure that you can see how the units work out for yourself, and then I'll put the answer back up when you resume. Alright, so we have our equation. The wavelength, the de Broglie wavelength, is Planck's constant over mass times the velocity. But we're given the electron traveling in miles per hour, so this makes this an even better dimensional analysis problem. So first thing we need to do is get from miles per hour into meters per second. Alright, so here's 4,500 miles per hour. Well, you have 1.6 kilometers in a mile, so you set that up that way to then cancel out the miles, you get kilometers. And then you have 1,000 meters in a kilometer, 10 to the 3 meters is 1 kilometer. Alright, the definition of an hour are 3,600 seconds, and 3,600 is really 60 times 60. 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600. Alright, then this equals about 2,000 meters per second. 4 sig figs, because we started with 4 sig figs. The kilometers conversion is not exact, but that has 5 sig figs on it. And then the 1,000 meters in a kilometer and the 1 hour to 3,600 seconds, those are exact definitions, so those wouldn't limit our sig figs. Alright, now we have the velocity of this electron in meters per second. So now we can calculate the wavelength. So we take the equation and plug the numbers in. Now again, the mass, you put this into kilograms. It's given to you in kilograms, so that's easy. But you do want the mass in kilograms. Alright, so 3.616 times 10 to the negative 7th joules, second squared, kilograms, meters. So you need the units to work out, right? So again, we expand the definition of a joule, and then, so this is why you need your mass to be in kilograms, because it's going to then cancel the kilograms that are in the definition of a joule. Alright, so after all the units cancel out, you're left with 3.6 times 10 to the negative 7th meters. And now double check, the problem is asking for wavelength in meters. Great, you have the wavelength in meters, you're set. You don't need to convert it again. Alright, so again, thinking about wave-particle duality, it's kind of a weird concept. Depending on how we look at it, we'll either see the wave nature or the particle nature of light or electrons or small particles. And again, it's because nature doesn't care what we think, it's going to do its thing, and how these particles exist, we don't have a relationship to it in our everyday experience. So, as an example, say, is this picture here a duck or a rabbit? You don't know, it depends on how you look at it. But it's both at the same time, and that's true for light and for particles. And so that's what we have for this video on the de Broglie wavelength.